Um, Good evening. Please let's allow some 5 minutes to see. 4 minutes from now to see if the others will join in. So if at 7:50 and then they are still nodding, then I think we can begin or we can commence the session. So please let's allow 4 more minutes. All right, so let's begin. So far we've done quite a lot. We've been able to cover everything and combinational circuits. And we're only left with decoders and encoders. And we've not just covered everything under them, but we've solved questions under all all those. So we presume that we are not only fit theoretically, but we also fit practically. In case we are to encounter any question under those fields. So we are going to continue in the same manner. So today we'll be looking at decoders and encoders. And then when we are done, we'll solve questions under them. We wouldn't spend a lot of time on that though. So what I'm going to do is that I'll contrast decoders and then encoders. I mean, we are going to study them side by side. And then when we are done, we solve questions under them just as we always do. So I anticipate, so I believe that by 9:20, the class should be over. I think one of us was sending out an info that's usually because of our work schedules, we get quite exhausted. So I'll keep everything straightforward and short so that we can close early and rest. All right, so let's start with decoders and encoders. All right, so with decoders, we can say that a decoder is any circuit, okay, that takes n inputs. So let's say it takes n inputs and then returns 2 raised to the power n outputs, okay. And its job basically is to I mean, it works in a similar manner as our multiplexers and our demultiplexers, but we said that with our multiplexers and demultiplexers, it takes the input and then it tries to convert it into the binary format and then compare it takes the selector signal, sorry, and then based on this the binary values of the selector signal, it compares it to the binary value of your inputs, okay, and then whichever it corresponds, it forwards it as an output. So we said that if your selector is showing or is displaying 0, 1, okay, then what will be selected is going to be D1. If it has 0, 0, what will be selected is going to be D0. If it has 1, 0, what will be selected is going to be D2. And if it has 1, 1, then what will be selected is going to be D3. This was a basic concept that we established under multiplexers and demultiplexers. But then if you were to understand, or if you did understand what you did under multiplexers and demultiplexers, then I will presume that encoders and decoders are going to be very easy for you, okay? Because it revolves around the same idea. Their operations are quite similar. Just that when it comes to encoders and decoders, we don't use select lines or we don't use selectors for our selections. Rather, we take the inputs and we try to, compare it to the corresponding output or try to forward it to the corresponding output. That is basically what we do. So let's illustrate that properly. So let's see, this is our decoder. So let me call it DEC. So this is a decoder. Assuming that our decoder has 2 inputs, let's call this I0 and let's call this I1. We said that the corresponding output is going to be 2 raised to the power n. So we are going to have 4 outputs in the format Y0, Y1, y2, and y3. So we have to ask ourselves, okay, what is the corresponding inputs for I0 and I1? Assuming I0 and I1 are both 0, 0, then Y0 will be selected. Okay. So if I0 and I1 are 0, 0, then Y0 will be selected. So let's do that properly. So we have inputs here, okay. And then we have outputs at the right side. So under our input, we call it I0 because in the diagram you can see I0 and I1. And our output is Y. So if our input is 0, 0, then Y0 will be selected. If it is 0, 1, then Y1 will be high. If it is 1, 0, Y2 will be high. And if it is 1, 1, then our output Y3 will be high. Okay, so you can see that this resembles our encoders and our multiplexers and demultiplexers in terms of truth table. Okay, just that with our multiplexers and demultiplexers, you cannot determine the Boolean expression without bringing your selectors. Okay, so selectors plays a very important role in multiplexers and demultiplexers, but here we don't use selectors. Basically, our input is what determines the outputs. All right. So let's understand this, or let's establish this fact. So this will be our truth table for our. We said our input is 2, right? And then our number of outputs are 4. So for a 2 is to 4 decoder. Okay. And now let us look at our truth table here and try to establish a fact here. We can see that for any set of input, let's say 0, 0, 0, 1, 1, 0, 1, 1, only one output is high at a time, okay, or is high per time for any input combination. So if our input combination is, let's say 0, 0, only Y0 will be high. That means only Y0 will be 1. Everything else will be 0. Okay. If our input is 0, 1, then we said only Y1 will be high, right? Everything else is going to be 0. If our input is 1, 0, then we know that corresponds to 2, right? So only Y2 will be high. Everything else will be 0. And then if our input corresponds to 1, 1, 1, we know 1, 1 is 3, right? So only our Y3 will be high. Everything else will be low. Okay. So we established this concept when we're looking at multiplexers and decoders. All right. So what we basically do is that we take the input, convert the input into the decimal equivalence of your binary. I mean your binary input. All right. And then you just note the corresponding output. You see the outputs are labeled Y0, Y1, Y2, Y3, etc., which are in decimal numberings. So if you convert your input into decimal, you're able to directly know the outputs that directly corresponds to your input, and that will be high. Apart from that, everything else is low. So a very important fact that we are to establish, or is to be established, is that when it comes to decoders, okay, only one output can be high per time. So you can see that here, when the input was 0, 0, only Y0 was high. Everything else, sorry, only Y0 was high. Okay, so I'm referring to this.
only Y0 was high, everything else was low. But when the inputs now became 0, 1, only Y1 became high because 0, 1 corresponds to 1, right, which is Y1. When the input became 1, 0, which corresponds to 2, only Y2 became high, everything else was low. And when the input became 1, 1, only Y3 was high, everything else is low. So from this, we can be able to establish a concept that for any given input combination for a decoder, only one output will be high per time. All right. So we can proceed with that. So we said that decoders basically, they take inputs as n and then they return output as 2 raised to the power n. But now let's, and please, we already know this concept and multiplexers and demultiplexers, right? But that one, n is rather our selectors or our select lines, okay, not our inputs. Let's look at something here, okay. We have a decoder that we call a BCD to decimal decoder, all right? And then one thing I want us to understand is that one of the functions of a decoder, okay, that it can be used to convert one number system to the other, okay. So for instance, if you have BCD to decimal decoder, what it does is that it converts binary coded decimals to decimals or to actual decimals. So you have something like this. Please, let's make this point interactive so that everyone is able to understand this. So you have, let's say, a binary coded decimal, which is BCD. Okay. So 3 inputs. This can be, let's say, 0, 1, 1. It can be 0, 1, 0. It can be 1, 1, 1. It can be whatever. So this is I0. This is I1. And this is I2. Please, can someone tell me how many outputs we are going to have here? If we are to follow the traditional method. All right, so if you have to follow the traditional method, you said we are going to use a formula n, which is our input. So this all this becomes our n. So what's our n? Our n is 3, right? Exactly. So we said that our corresponding output will be 2 raised to the power n, right? Which is, in this case, our n is 3, so 2 raised to the power 3. So we are going to get 9, okay? We are going to get 9 here. But for this particular type of decoder, 9 cannot be true for the outputs of this decoder because we are converting BCD to decimal. And you know that decimal exists in how many digits? Please, can someone tell us how many digits does the decimal exist in? Or how many digits does decimal numbers have?
0 to 9.
Please come again. Hello. Please, can someone help us? How many digits do decimal numbers have? Please, am I audible?
Yes, we can hear you, sir.
Oh, okay. All right. So please, how many unique digits does a decimal number have?
0 to 9.
0 to 9. Perfect. So we have 0 to 9, right? So 0, 1, 3, and this continues up to 9. So in total, we have 10 unique digits, right? So 0 is the first, 1 is the second, 2 is the third, 4 is the fourth. 3 is the fourth, 4 is the fifth, 5 will be the sixth, 6 will be the seventh, 7 will be the eighth, 8 will be the ninth, and then 9 will be the 10th, right? So we are going to have 10 outputs here for a BCD to decimal decoder. because we can be able to get 10 set of digits here as our output. Okay, so we have our output as y0, we have y1, we have y2, and this continues up to y9. So you can see that in this case, our number of inputs are 3, but our output is now 10. Okay, and we can see that this here does not agree. This here basically does not agree with the concept that our number of outputs, our number of outputs, let's say n is our number of outputs will be equal to 2 raised to the power our number of inputs. Okay, so you realize that this here does not agree with this. So there are exceptions to the thing. Okay, and it is not always the case that the formula inputs is equal to, outputs is equal to 2 raised to the power our inputs. Okay, this does not always hold. Okay, and this is not the only example where this does not hold. Other decoders like 3 to 8 decoder. Okay, so 3 to 8 decoder has 3 inputs and 8 outputs. We will look at that also. Has 3 inputs and 8 outputs. But if you try to take 2 raised to the power 3, you are going to get 9 instead of 8. So you can clearly see that there are exceptions to the thing. Okay. So let's kindly take note of that. So we can have several types of decoders. Okay, we've talked about the BCD to decimal decoder. We've talked about the 2 to 4 decoder. We can have several others. Okay, several others, just as we did for multiplexers, demultiplexers. Okay, you can just take the inputs, the number of inputs, square it, and then you get a corresponding output, and that gives you a valid decoder. All right, so let us look at other things. Let us look at other things here. So I spoke about the uses of a decoder, right? So we can use decoders for code conversions. Okay, so to convert one code to the other. All right, like converting a BCD to decimal, like I just illustrated. We can use a decoder to do it. So let's try and then simulate the entire process of converting a BCD to decimal. Okay, so to do this, we are going to take a BCD to decimal decoder, the block diagram. We are going to look at the corresponding truth table, and we'll try to look at its expression or its corresponding expression, and if possible, how the diagram should look like. So we are talking about a BCD to decimal decoder. So BCD, then we have decimal. Okay, so let's take our inputs. We have I0, we have I1, we have I2, then we have I3. So we are going to have, we said we are converting to decimal. So decimal has a total of 10 unit digits, so we are going to have 10 outputs. So let's say the outputs are going to be Y0, Y1, Y2, Y3 up to Y9. Okay. So we are going to have our inputs, which is Y0, I0, I1. We will have our I2. We will have our I3. And then we are going to have the corresponding outputs, which are going to be from Y0, Y1, Y2, Y3, Y4, Y5, Y6, Y7, Y8, Y9. Okay. So that's the input and then the corresponding output. Okay. So just as we explained, we are going to look at our input combinations, and from our input combinations, we'll be able to denote the corresponding output. So assuming this is 0, 0, 0, 0, you know our Y0 will be high, right? And if Y0 is high, then automatically everything else will be low, because you said for decoders and encoders, only one output can be high per time. That's for a decoder. So we can have 0, 0, 0, 1, and then we are going to have Y1 being high, right? Then we can have 0, 0, 1. Yeah, maybe. Please, a minute. Yes, you're asking a question. Yes,
So you said why one be selected?
yeah, that's for 0001. Y1 will be selected because 0001 corresponds to 1, which is
Okay.
Y1.
Okay.
Then we have 0010, which corresponds to Y2. Then we have 0011, that corresponds to Y3, etc. Okay, please, a second, I'm coming. Okay, so let's continue. So that will correspond to Y3. So you just follow suit in that manner. Okay. So whatever you are looking for, or to a lot of possible set of how do you call it? Combinations are achieved or attained. Okay. And that would most likely end this as the ninth set of combination. All right. So let's properly look at that and examine its diagram. So that's that. Okay. So we're on the BCD to decimal decoder, right? I believe we have that. Oh, unfortunately, I think we don't have that here. But let's examine what we have here. And let me use that to explain. Wait, it's not structured. Because I'm coming in a second. All right. I think we don't have the BCD to decimal decoders here. All right, so let's progress. All right, so you can see here we have the two to 4 decoder. So we said that it takes 2 inputs and the corresponding output is 2 raised to the power n, which is 2 raised to the power the number of input. That gives you the corresponding outputs. So we denote we've already drew the truth table for this. So we said A and B are the inputs, okay? So the set of all possible combinations for A and B are 0, 0, 0, 1, 1, 0, and 1, 1. And we said that if 0, 0 is R input, then Q0 will be selected, which is output 0, okay? When our A and B is 0, 1, then Q1 will be selected, which is output 1. And then if we have 1 and 0, 1 and 0 we know is 2, right? We are going to select our output 2. And if we have 1 and 1, we know this is 3. So this is 0, this is 1, and 3 will correspond to our Q3. So that's basically how the truth table is derived. And we also established that at every point in time, only one output will be high, okay? Everything else will be low, okay? So we can also see that right here. And so this is a corresponding truth table. Let's look at how the corresponding circuit diagram. So let's look at how the circuit diagram is drawn. So let's create an additional field here and call that C expression, that's E, okay, for the Boolean expression for that. So for Q0, we cannot see here that here only Q0 is high, and Q0 is high when A is 0 and B is 0. And we all know that when A is 0 and B is 0, it corresponds to A prime and then B prime. When Q1 is 1, it corresponds to A0 and B1, which is A prime or A bar, and then B. And then when Q2 is high, it corresponds to 1, 0, which is A, B bar. And when Q3 is high, it corresponds to 1 and 1, which is A, B. Please, I believe we all got that right. Please, I believe we all got that.
Yes, sir, I'm following, sir.
Okay. So now, after we've obtained this,
So
we can see that.
there's an up.
Okay. Yes, please. Your question.
It's a free man.
Sorry, it was a mistake. Sorry.
Okay. So we can see that for Q0 is A prime and B prime, right? So we are going to use an AND gate to implement this. So we are going to use an AND gate, and then this is A NOT, right? So we use an inverter right here, which is a NOT gate for our A, and then another NOT gate for our B, and then we have A and then B right here. All right. So here for our A prime and B, we are also going to we have an AND gate again, but then the A right, but then the A is not, so we have a NOT gate right here, and then we have our B. So we are going to do the same for our A and then B bar, and the same for our A and then B. So in total, we have 4 AND gates, okay, being used to implement this. So you know the other method for doing this, we can just have our A and then B, and then denote the nodes of those. Okay, and then we do the same thing for B, and then we just connect them to that. So either of the two methods, we are fine. All right, so here you can see the logic gates right here. So this represents Q0, which is A bar, B bar. This represents Q1, which is A bar, B. This represents Q2. This is A, B bar. And this represents Q3, which is A, and then B, okay. And then we have our inputs right here. All right, so that's just how to draw the diagram. So most likely, I am not so sure whether you are going to have diagrams, since our mode of examination is online on site. I'm not so sure whether you are going to have diagrams in there. But even if you are going to have diagrams, you'll not be asked to draw the diagram. So what you should know is to know how the diagram came by and the properties of the diagram. I mean, for example, the number of AND gates. We saw similar such questions under multiplexers and demultiplexers, right? So you have to just know how many, probably how many AND gates, NOT gates, etc. that were used to build a circuit, etc. Okay, those basic stuff. So here we have decoder with enabled input. Okay, that's an enabler. So under the multiplexers and demultiplexers, we said that sometimes an enabling input is applied, right? So enabler input is used, okay, or is implemented with an AND gate to either switch the entire circuit on or switch the entire circuit off. So the enabler basically functions as a gate, okay? So it functions as a gate that determines the state of the entire circuit. So if the enabler is on, the entire circuit is on. So let's say we have our input as A and B. And then you have one more input, which we are going to call E. So let's label this as E. So the E is originally not part of the input. It is just an enabler, which determines the state of the circuit, whether the circuit is on or off. So we said that if the enabler is on, then the entire circuit is transparent. That means if you give it input, it should be able to give you an output. But when the enabler is off, then the entire circuit is down. All right, or the entire circuit is in the off state. That means that even if you give it input, it is unable to return output. Okay, so the state of the enabler will determine the state of your entire circuit when applied. Okay, so the enable input pin allows the decoded output to be turned on or off by applying a logic 1 or logic 0 respectively to it. When the enable input is at logic 0, which is enable is equal to 0, all outputs are off. Please, let's take note of this. So all outputs are off, okay, for AND gates, regardless of the states of the inputs. So when our enable input is off, which is enable is equal to 0, all outputs are off. That means even if you give it an input, the device is unable, or the circuit is unable to return an output. But if the enable is equal to 1, or if En is equal to 1, then the circuit is able to return an output if you feed it with an input. Okay, so we are going to look at some terminologies. I mean, we have something we call a transparent circuit. Okay, so a transparent circuit is any circuit that is capable of returning an output immediately an input is fed to it. All right, so we said that a transparent circuit is basically a circuit that is capable of returning an output immediately an input is fed to it. So whenever we feed that circuit with an input, it should be capable of returning an output. We call those kind of circuits a transparent circuit. All right, that isn't really a classification of circuit per se, but it's a state of the circuit. It is used to express the state of the circuit. Okay, so if the enabler is 1, we can say that the circuit is transparent, meaning that when you feed it with input, it should be capable of giving you output right away. All right, so okay, when you get to sequential circuits, we are going to look at gated circuits. Okay, so some circuits are also gated. When we use enable inputs, they are usually gated. So that one, the state of the gate determines the state of the circuit. So when the enable is 1, the entire circuit is transparent. When the entire enable is 0, the circuit is not transparent. Okay, that means that when you give it input, it will not be able to return an output. So generally, to implement this enable function, the 2 inputs AND or NAND gates are replaced with 3 inputs AND or NAND gates. Again, you would talk more about how the enable works when we get to sequential circuits. Okay. So let us look at the diagram here. So this diagram is the same diagram as our 2:4 decoder. But now we've added the enabler input. Please, can you all see that we've added the enabling input, which is En. So please don't be confused. Yes. This is the same. You have your A, you have your B, and then you have the corresponding outputs. That is Y0 to Y3. Okay. But now we have En added, which is our enable. So we assume that this circuit is gated. Okay. And it is protected with an enable. So the state of the enable depends or determines whether the circuit is functioning or not. So we said that if the enable is 0, that means that the entire circuit is low or is off. If you give it input, it cannot process the input. So if the enable is 0, we don't care what the input is. The output will be 0, which is it will return its previous state, or it will only read from memory. It cannot process any of the current inputs. So when we say that the A and B, we don't care what it is. It can be 0, 0, it can be 0, 1, it can be 1, 0, it can be 1, 1. It does not affect the state of the circuit because the enabler is off. Are we together?
There is
So what you
your
are
hand is
saying,
Please, I
okay,
have a question.
all right, please, right.
Please, with the position of the enabler, when it changes, okay, let's assume that maybe there's a change in the position of the enabler. Will it affect the output?
No, the enabler does not technically affect the output. It just functions as a gate. Okay, so it determines the state of the entire circuit, not really affecting the output. So if the enabler is off, it affects the functionality of the circuit by making sure that it is unable to process inputs. Okay, so if the enabler is off, yes, we can say in a way that it affects the output by ensuring that the inputs are not processed at all. So the input becomes don't care. No matter, we don't care what the input is, the output will always be 0, 0, 0, 0 because the entire circuit is off. I don't know if you are getting me. But it is not always the case that the output will be 0, 0, 0. Let's take note. It will read from memory. The current value that is stored in the circuit is what the circuit will keep on displaying, or the circuit will display. So if, let's say, already the circuit had an output of, let's say, 0001, then that 0001 will still be held. Sorry, please, we are dealing with combinational circuits. If we are dealing with sequential circuits where memory elements are applicable, that will hold. Please, sorry, forgive me. For combinational circuits, immediately an operation is done, the entire circuit refreshes, or it just throws away all its previous operations. You don't recount previous operations. So then no memory element is applied. Hence, we do not take into consideration what is kept or stored in memory. So kindly forgive me with that. So that means that if our enable is off, our input is don't care, our output will automatically be 0, 0, 0. But if this was to be a sequential circuit, then it's going to read from memory instead, since we assume that something has been stored in memory. Okay. But since we are dealing with combinational circuits, or a decoder is a combinational circuit, it does not have a memory element. So the output is going to be 0, 0, 0. But we can see here that if the enabler is 1, then the circuit is functional. That means that the circuit is capable of processing its inputs. So when you give it 0, 0, 0, 0, it is able to indicate that Y0 is high because 0, 0 corresponds to Y0. If it is 0, 1, we know 0, 1 corresponds to Y1. If it is 1, 0, we know 1, 0 corresponds to Y2. And we know 1, 1 corresponds to Y3. So the circuit will function normally. It maintains a normal behavior. Okay, the circuit maintains a normal behavior when the enabler is on. Okay, when the enabler is on, that means that the circuit will function normally. It does not basically impact the behavior of the circuit, aside from the fact that it can toggle its states. It can put the entire memory into an on state, the entire circuit into an on state or an off state. So please, let's take note of the enable input. So sometimes they can give you a tricky question. Like, let's say a decoder, let's say a 2:4 decoder has inputs 0 or 1. What will be the output of that decoder? And then they'll give you A, let's say Y1, B, Y0, C, let's say B, Y2, C, Y3, and D, let's say they give you something like 0, okay, then you go for D, because you know that once your enabler, once the question specifies that your enabler is 0, so let's say the input is as A is 0, B is 0, and then enabler is equal to 0, then automatically you should know, or the only option you should be looking to select is 0, okay? Or if they give you Y0, that's also no, not even Y0, please, not even Y0, because Y0 suggests that Y0 is 1. But since the memory is not, the circuit is not functional, everything is going to be 0, okay? So the only correct answer there is 0. All right, so that should be the answer you should select. So know that the status of the enabler affects the functionality of the entire circuit. So we can see how the enable inputs works, right? So we can see the same diagram for our 2:4 decoder, but an enable input is applied, okay? And we said that if you feed this enable input to 0, the entire circuit is in an off state, meaning that the only outputs it can display is zeros, nothing else. It's unable to process its input. But if the status of our enable input is 1, then the circuit is now live. It can be able to process any input that it is fed with. So we can see that these are 2:4 decoder. All right, so we have a problem here. So let's see if we can work on that problem. The problem says that construct a truth table for a 3:8 decoder, and then design the appropriate circuit diagram for the truth table constructed. So how do you solve a problem like this? Or what is the ideal solution for a problem like this? We have a 3:8 decoder. So you know 3:8 decoder has 3 inputs, right? So let me draw it on a fresh page. Now let me just use this, okay, so that we save time. So we have a 3:8 decoder. It has 3 inputs. So let's label the first input I0, I1, I2, and then the corresponding output is 8, right? So you have Y0, Y1, Y2, and then this continues up to Y7, right? Are you together? This continues up to Y7 because you know Y0 is 1, Y1 is 2, Y2 is 3, Y, etc. We count in that manner, and Y7 will be our 8th output. So it is going to be 3:8. So when drawing the truth table, we are going to have 3 inputs, right? Which is I0, I1, I2. Or someone can decide to use ABC. Okay. So if you decide to use ABC as your inputs, let's say A, B, C to correspond to or to represent your inputs, then the truth table we are going to have A, B, C. And then the output we are going to have Y0, Y1. I think I'll address a very critical question here. Okay, that's the critical question of where do you stop? So Y3, Y4, Y5, Y6, and then Y7. Okay. So with this, we are going to take our A, okay, and then assume that this is we have 0, 0, 0, right? So 0, 0, 0, that's going to correspond to Y0, right? So we have 0, 0, 1, that is y1. We have 0, 1, 0. That's our y2. We have our 0, 1, 1. That's our y3. Everything else will be 0. That's why I'm not even bringing it. Then we are going to have what? Our 1, 0, 0. That's going to be our y4. We have 1, 0, 1. That's going to be our y5. We have 1, 1, 0. That's going to be our y6. And then we are going to have 1, 1, 1. Am I right? That's going to be our y7. Okay. So now we've been able to address all our inputs from y0 to all our output from y0 to y7. So there is no need continuing again. Okay. Don't say that because you have 3 inputs, so you keep, no. Because if you use a normal truth table formula, you have 3 squared, which is supposed to give you 9 combinations, right? But here you've gotten to the 8th combination and all your outputs have been addressed, so you end. So this is literally going to be the truth. Fill the rest with zeros, and then you're okay. So this is the corresponding truth table. Now you take each of your outputs, y0, okay? And then you ask yourself, what is the corresponding Boolean expression for y0? You know, y0 is 1 when A, B, C are all 0, 0. So for y0, we are going to have A prime, B prime, and then C prime. Okay. And then we are going to take our y1. We know y1 is high when A is 0, B is 0, and C is 1. So we are going to have A prime, B prime, and then we are going to have what? C. And then you know y2 is high when A is 0, B is 1, so we have B, and then C is 0, so C prime. And then we continue to do it for all the input combination. And then we are going to have the expression for y0, y1, and then y2, etc. Okay. And from there, we can proceed to draw our circuit diagram. So we know that we are going to use ABC as input. Okay. So ABC as inputs, and then we denote their prime values. Okay, so here is A prime. We are going to do for B, do for C, and then we can proceed to draw the circuit. Please, I hope we are all okay with this. Please, I hope we are all okay with this. All right, so I think we have the question answered here. Exactly. So we have the question
please, I have a question.
Okay.
I have a question on, I think you cited an example. And this afternoon, I was going through some past question and I met this question. It's under the encoder.
Okay.
So should I read out the question?
Okay. So you are you said. So it's like you saw a question, right?
4 bits. Yes.
Okay.
Can I read it out?
I'm listening to you.
A 4-bit priority encoder has input D0, D1, D2, and D3, where D3 is the highest priority. If D3 is equal to 0, D2 is equal to 1, and D1 is equal to 1. Then D02 is equal to 1.
Okay.
What is the binary output?
What is the binary output? Is that
Yes,
what is the
please.
binary? What? Okay, so
A
that's what
was
the
We didn't hear the question. We didn't hear the question.
okay. Let me restart.
question.
So a 4-bit priority encoder has input D0, D1, D2, and D3, where D3 is the highest priority. Full stop. If D3 is equal to 0, D2 is equal to 1, D1 is equal to 1, and D0 is equal to 1. What is the binary output? Then the options were given. A was 0, 1, then B is 0, 0. C is 1, 0, then D is 1, 1. Please, I hope you had a question right.
Yeah, I got the question right. Okay, so I think we are yet to get to priority decoders, but when it comes to priority or when you take priority decoders, basically it gives priority to the highest input. So if just as said, D0 to D3, D3 takes the highest priority, and they are usually used in terms like for instance, lift systems, okay, where people can press two inputs. So at a time, we see that if you look at the normal decoder, I mean, we said that only one output can be high at a time. But when you come to the practical world, in the practical application of decoders, let's say in a lift system, you can have let's say a case where two people, one person will enter into the lift and then he will press one. So he will press, let's say, two, and then Y2 will be high, or he will press a particular input combination corresponding to the floor that he's moving to, and then this will be high at that time, which means Y2 will be high. Another person joins, and then he presses another combination, and then now you have Y4 being high. Okay, so you have two different input combinations being high per time. So a priority has to be set, and the priority usually set at the highest option. So this question was saying give the combinations for your inputs, right? And was asking that what will be the binary value. So basically, it was trying to ascertain where the priority will be set. Okay, on that. So when you get to priority encoders, you illustrate that for you. Okay, so please kindly hold the question. Let's get to priority encoders and then we address the behavior for. So we have BCD to decimal decoder. So I think BCD to decimal decoder also have talked about that, right? So you have these are your inputs. You have 1, 2, 3, 4, right? So these are your inputs, and then you have the outputs corresponding to 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. And the reason why we end at 9 is because we know that by decimal numbers end at 9. So decimals begin from at 0 and then end at 9. Okay. So that is that for it. So I wouldn't stress much on this since you've already spoken about that. So it has 4 inputs and then 9 outputs because the decimals have 9 unique digits, and there's a corresponding truth table. Our input is going to be our 4 inputs, which is A, B, C, D. Okay, and then our output is going to be from 1 to 9. So if we have 0, 0, 0, 1, that's going to 0, 0, 0, 0. I mean, if you have 0, A being 0, B being 0, C being 0, D being 0, our y0 or our output 0 is going to be high. If you have 0, 0, 0, 1, your output 1 is going to be high. 0, 0, 1, 0 will correspond to output 2. 0, 0, 1, 1 will correspond to output 3. 0, 1, 0, 0 will correspond to our output 4, etc. Okay. So all your outputs are addressed. Sorry. All right, so this is going to be the circuit diagram for a 3 to 8 3 to 8 decoder. Okay, and it just stems out from the resulting expression. So let's try and then deduce the expression for, let's say, 2 or 3 of them. Okay, so to deduce the expression here, if you take y0, okay, y0, you can see that the corresponding input that makes y0 high is when A is 0, B is 0, C is 0, and D is 0, right? So we are going to have A prime, B prime, C prime, and D prime for y0. So if we come down here, let's come down here. Let's come down here. You can see this is D0, right? And D0, check. This is you have your A, you have your B, you have your C, you have your D. Okay. So you can see that D0 can be traced to the prime. You can see that all these are inverted. You can see them here. So you can trace this to the inverted values of your input, which is A, B, C, and D, which corresponds to A prime, B prime, C prime. And the type of gate is an AND gate, right? Because all those terms are product terms, so we use AND gates. If you come here, you have A, then B prime, C prime, D prime. So you come and compare this to here. So you can see that you have A, only your A is 1. So you can see that only your A does not have the not here, okay? Meaning that here you have A, and then you have B prime, C prime, and then D prime, okay? Then you go to the third line. The third line is what? You have A prime, then B, then C prime, then D prime, okay? So you have A prime, then B, then C prime, then D prime. If you come down here, you see that you have A prime, right? So you can see that your A is prime, then you have B is not inverted, then your C and D are also inverted. So we follow same method to deduce the expressions one by one. And after deducing the expressions, we can now draw the corresponding gates based on the expressions that we have here. Okay. So yeah, if you get a question like maybe for a 3 is to 8 decoder, okay, when y2 is high, what will be the corresponding Boolean expression, or what is going to be the corresponding expression or function? You just have to know that y2 is high when your y2 is high when you know you are dealing with your y2 is high when you have this particular input combination, right, which corresponds to, okay, so you just deduce it. So you have A prime, you have B prime, then you have C, and then D. Okay, in that manner. So let's move on. So we have the 7 segments display decoder. So the BCD to 7 segments display decoder, we have 4 inputs, okay? And then we have a total of 7 outputs, okay? And the 7 outputs corresponds to this right here, okay? So it corresponds to this. Our first output corresponds to our A, second output corresponds to B, second output corresponds to C, third output corresponds to D, fourth to E, fifth to F, then C to G. No, I've missed something. So first output corresponds to A, second to B, third C, fourth D, fifth E, sixth F, and then seventh G. Okay. So what happens is that if our, let's say, if our A is let's say if our A is 0, our B is 1, our C is 1, our D is 0. Okay, we are going to denote the corresponding outputs, and I'm going to show you how to denote the corresponding outputs in a moment. Okay, so let's look at the truth table right here, and let's study the behavior. Okay, so you have the decimal digits. You have the input lines, which is A, B, C, D. Okay, and then you have the output lines, which are up to 7. So you have 1, 2, 3, 4, 5, 6, 7. Okay. So if, please, let's look at this carefully. So if our input is 0, 0, 0, 0, that corresponds to 0. So let's put that here. Our input is 0. Okay. So 0, we know 0 in BCD. We are going to get 0, 0, 0, 0, right? And this corresponds to 0. Now, if we want to represent 0 here, we know that our A will be high, right? So our A will be high, which is 1. We know that our B will be high, B will be 1. We know that our C will be high, C will be 1. We know that our D will be high, D will be 1. So we know that our E also will be high, E will be 1. We know that our F will be high, F will be 1. But our G is going to be low because 0 will look like this. Something like this, okay? We don't cross the middle. So all the A, B, C, D, E, and F is going to be high in the exception of our G, okay? So you realize that right here, everything is high in the exception of our G, just as you illustrated. So for 1, our BCD is going to be 0, 0, 0, 1, right? So we have one is going to correspond to let me see, 0, 0, 0, 1 as our inputs. Now let us look at the outputs. We know that 1 is supposed to look like this, right? So our B is going to be high. Our C would also be high. So you can see that right here. Our B will be high. our C also will be high. Okay. So now if you come to 2, 2 looks like this. Okay. So here is A, here is B, C will be low, D will be high, E will be high, F will be low, J will be high. Okay. So we are going to have A, B, D, E, and J being high. So we have A, B, D, E, and then we have our J being high. That is how we would obtain our 2. So we use that same method to obtain all the rest. Okay. So please, any question there before we look at encoders? So for encoders, I'm only going to brush through because it's just the opposite of decoders. And I think at encoders, you can be able to address the priority question there. Please, are we okay so far?
Yes, we are following.
Okay. All right, so our encoders works in the opposite, has an opposite behavior to our decoders. Okay. So they are used to store information or data, transmit more data from source to destination, detect errors in data transmission easily, and to enhance speed of data transmission. Okay, so we said that in our decoder, we are going to say 2 is to 4 decoders. But when it comes to encoder, we have the opposite of it, which is rather the 4 is to 2 encoder. Okay, so 3 is to 8 decoders. Here we are going to have an 8 is to 3 encoder. Okay, so BCD to decimal decoder, we are going to have a decimal to BCD decoder, etc. So it's just the opposite of a decoder. Once you understand a decoder, inverts the logic and you have an encoder. So we said that a decoders have, if a decoder has n input, it is going to have a 2 to the power n outputs, right? This is what we said. But we said that there are exceptions. There are cases where our output is going to be less than 2 raised to the power n. Hence, we say that our outputs, right? So let's call m our outputs is going to be less than equal to 2 raised to the power n in such scenarios. Please, let's always look out for this in examination when it comes to decoders and encoders. If they ask you the correct relationship between input and output, it is actually m less than equal to 2 raised to the power n. Because you know that in some cases, our output will be equal to 2 raised to the power n. But in other cases, our what's that? So in other cases, our output will not be equal to 2 raised to the power n, but it's actually going to be less than 2 raised to the power n. Please, I'm coming. Okay, let's continue. Let's continue. So let's always look out for this. Okay. So let's continue. So you can see our 4 to 2 encoders. So 4 to 2 encoders will have 4 inputs because our 4 rather becomes our input now and 2 becomes the output. Okay. So our output, we take our output, we have 0, 0, 0. It's just the same thing as the truth table for the decoder, but we just invert it or swap the position of the input and output. So they are the same, just that we bring the inputs. For decoders, this input here, A0, A1, A2, A3 will rather be at the output position. And then the output B0, B1 rather be at the input position, okay? So you just do the swapping psychologically and then that's the same thing, okay? So it's just the opposite of one another. So just take the your inputs for your decoder and then you make it an output for your encoder, and then your output for decoder becomes your input for your encoder, etc. All right, so we have these 4 types. You have the octal to binary encoder, you have the hexadecimal to binary encoder, decimal to BCD encoder, and then you have priority encoder. So all these things, I think we've looked at their correspondence and at the decoder. So let's move straight away to the priority encoder. So look at what they are. So a priority encoder is an encoder circuit that includes a priority function. The operation of the priority encoder is such that if 2 or more inputs are equal to 1 at the same time, the input having the highest priority will take precedence. They are often used to control interrupt requests by acting on the highest priority first. We could design 4 to 2 priority encoder, 8 to 3 priority encoder, and 16 to 4 priority encoder. So you see that we earlier gave a scenario that you can apply an enable, right? And then it changes the behavior of the circuit. Otherwise, you can also add priority, okay? So this is the priority right here. So if assuming that we assign a priority of 0, okay, to that particular circuit, then it just works in a similar manner as our enable, okay? So all our input here becomes don't care. And then directly everything goes down. If you assign a priority of 1, everything works as it's supposed to be. But let's take note. We said that if 2 of the inputs are high, it assigns priority to the highest or to the highest input, right? So in this case, this is 1 here, this is 1. So anything before becomes a don't care. We don't really care if it is 0 or if it's a 1. We said that we only assign priority to our highest output, okay, which in this case is this. So once you're able to locate our valid or our highest, our output to the highest priority, anything before becomes don't care. We don't care whether they are really 1. We don't give it any priority at all. Please, I don't know if you are okay with this. Or if I should break it down a little further. Yes, please, are you okay with this?
So please, so all the X over there, all of them are representing the don't care.
Exactly, don't care. That means you don't care what our input there is. Our input can actually be 1. We don't really care. But then the corresponding binary value will not change. Okay, because we know that our input here is we have 0, 0, 1, and then a don't care. So in this case, the first one, okay, takes priority. Anything that follows, we don't care. If it's even, look, this can be a 1. If this is a 1, we are saying that according to the concept of priority encoders, we give priority to the highest input, right? Or to the input with the highest priority, which is the one which is closest to our MSB. So once we locate that, all the rest becomes a don't care. We don't really care whether they are 1s or 0. So far as we are
Okay.
giving priority to this, everything else doesn't matter again.
Please, so you see where the 0 1 is 0 1 0 0, then the VIN. So under the 0 1, I can see there's a don't care. Then after that, there's another don't care.
Yes.
Can you explain that one a little bit?
All right. So let me take my time and let me explain this thoroughly, okay, so that we understand. I think the reason why I'm moving fast is because I presume that you already understand the truth table from decoders. So let me explain what this truth table means. So this truth table is a 2, it's a 4:2. So 4:2 encoders, right? So he said that usually a 4:2 encoder will have 4 inputs, right? So we have 4 inputs, so I0, the I here represents input. So we have input 0, input 1, input 2, and then input 3. Okay. So we have 4:2 encoders. So we have input 0, input 1, input 2, input 3. And then we have their corresponding output. So we said 4:2. So how many outputs would they have? 2 outputs, right? So let's call that Y0 and then Y1. Okay. But now you want to apply priority. Okay. So let's assume that we apply priority to this. So V denotes priority. Okay. So when it's 0, it means that that particular set of combinations has no priority at all. So that one, the output takes don't care. Okay. Because no priority at all is applied in those. So our input becomes 0, 0, 0. And then our output is a don't care. That is for this. Okay. So let's assume, or let's make the assumption that our input now is 0, 0, 0, 1. Okay. Our input now is a 0, 0, 0, 1. What is going to be the correspondence here? We know the correspondence is going to be 0, 0, right? Because we studied earlier. Look, just think about this from the perspective of a decoder. Okay. Just imagine this is your input. We said that if you have 0, 0 here, okay. I'm coming, please. Let me confirm something here. Yeah. So we said that under our decoder, if you have a 0, 0, then it will correspond to D0. D0 becomes high, right? So do you remember that? So now, if this is 0, 0, then please forgive me. Let me label this properly. This is supposed to be input 1, input 2, input 0. Okay, input 1, input 2, input 3. They've been flipped. But let's just continue. So this here becomes 1. Okay, if here is 0, 1, let me just label it fully. So you have 0, 0, 0, 1, 1, 0, and then you have 1, 1. So this here will be 1 because D0 will be high. If it is 0, 0, 0, 1, you have your D1 will be high. Okay, so 0 here, 1, 2, 3. Okay, so if you have 1, 0, D2 will be high. And if you have 1, 1, D3 will be high. Okay, so you have something like this. Okay, so here, the reason why the circuit is able to function normally is equals to apply 1 to our priority, which functions as our enable in this case, okay? So now, so let's study this carefully. We said that in a priority encoder, it assigns priority to our highest input, which is the one which is most closest to our MSB. Okay, so here you see that this is 1. Here, this is 1, this is 1, this is 1. Now, assuming that this is an elevator, okay, an elevator, someone came and then entered a particular input here, which sends this high, okay, that's room 2. Someone also came and then the same elevator entered room 1, okay, which is 1, right? Or let's say floor 1. So we are saying that we give priority to the highest one, which is 1. So if we give priority to this, now we don't even need to know what the previous one is. We don't really care what it is, okay? It doesn't take priority. So if it is 0 or if it is 1, we don't care. What the elevator is looking at is this particular input that has been entered here, okay? So if 1 is selected here, then has been entered here. That's the highest one here. So everything before that one will not be given priority. So everything before will not be given priority, except this ones here. Okay. So now, please, can you kindly read your question again, and then let's look at what the answer will be.
Okay. So a 4-bit priority encoder has inputs D0, D1, D2, D3, where D3 is the highest priority. Full stop.
Okay.
If
So D3,
D3
D3 will correspond to our I3 here, and D0 will correspond to our I0 will correspond to our D0 in your question. Okay. So realistic.
if D3 equals 0, D2
So
equals
D3
1.
Okay.
D2 equals 1, D1 equals 1, and D0 equals 1. Please, should I continue?
So continue.
What is the binary output?
All right. So what is going to be a binary out? So we have to ask ourselves the question that which one here? Okay. So we have D3 is 0, D2 is 1, D1 is 1, D0 is 1. Okay. So now the question is that which one has the highest priority? We all know that it is this one, right? Please, can you see that?
Yes.
And everything that follows is a don't care. So we don't really care about this. We don't care about this. So the corresponding binary for this particular combination is our 1 0. Okay. No, it's our 0 1 because this has been arranged as 0 and then 1 from the other direction. So please, what do you have as your options? Please, what do you have as your options?
So we have
Hello. It seems your line.
seems your line is. Can you hear me?
Yes, you can hear me now.
You can hear me now.
Yes, sir.
So A is 0 1, B is 0 0, C 1 0, and then D 1 1.
All right. So I think I would go for 09. Please, what's the correct answer there?
Let me check. A minute to check the answer.
First, check the answer. No, I think it should be 10 instead, please. It should be 10 instead because 01 here is representing NEC. So 10, 10.
Okay, so the correct answer is 10.
It's 10. Exactly. So you can see that
And
right here.
they give a reason. They give a reason that it says that since D3 is 0, the next highest active input is D2. The output for the index 2 is binary 10.
Yeah, exactly. So basically, without drawing your truth table, you can be able to know the answer by putting down the combination. So you have 0, 1, 1, 1. You know that this your one here takes takes the highest priority, right? And then anything before doesn't really matter. So everything before we can just sideline it. So you just have to look for your corresponding inputs that corresponds to this, right? And you know your inputs are going to be in the form 0, 0. You know 0, 0 is D0, right? You have 0, 1 corresponding to D1, and you know D0 will be 0, 0, 0, 0, right? No, 0, 0, 0, 1. Okay, D1 is going to be 0, 0, 1, 0. And you know that D2 is going to be 0, 0, 1, 1, 1. Okay. And you can see that D2 in this scenario perfectly corresponds to the input combination that they gave you, right? Do you recall? Which is 0, 1, 1, 1. Please, can you see that? Perfectly
Yes.
corresponds to 0, 1, 1, 1. And so you know that D2 is originally you have 0, 1, you have 0, 0 for D0, 0, 1 for D1, and then 1, 0 for D2. So you know that 1, 0 is your correct answer. Please, did you get the methodology?
Yes, please. I had your explanation. Thank you very much.
So yeah, octal to binary priority encoders also behave in a similar manner. And then that is it for decoders and then encoders. So they are just opposites of each other. Once you're able to understand the behavior of one, you are directly able to also understand the behavior of the other. You just have to invert it and then okay. Cool. All right, so I think our time is up, so we might not be able to solve questions today. However, I will entreat us all to go and solve the questions ourselves, and then tomorrow when we meet, we will solve. Please, we will spend a very, very short time to solve the questions, and then we'll start sequential circuits. I really want us to finish about half of sequential circuits tomorrow, okay? And then tomorrow is Friday, right? This is tomorrow Friday. Yeah, tomorrow is Friday. So we should finish about half of sequential circuits on Friday. And then on Saturday, we can use like from the morning up to evening. I mean, to complete sequential circuits and then to clear as much as we can at finite state automata. And then we can solve questions. I mean, for Saturday night here, the only thing we are going to do is to solve questions from the first section to the last section, and then we can bring 203 to a halt. But look, I'm very positive that if we've been able to follow and then do our own revisions properly or adequately, we shouldn't have a problem. We shouldn't have a problem with whichever questions that we are asked in the examination. Okay. So please let's solve the questions. Let's solve the questions so that tomorrow when we come it to be very, very fast. Please, those who don't really know the link that we used to solve questions, I'm going to put it again on the platform. We have a particular site where we solve or we take our questions from. So please let's let me get the questions right now. The questions link right now, and then it's on the platform. Please, any question or anyone has a contribution or something to say? Okay, so we have all right, so I'll drop that on the platform shortly for us so that we can work on it on now. All right, so have a wonderful evening. We'll meet again tomorrow.
Okay, thank you very much.